So now we have that the average force exerted by a gas molecule due to the collision with a given wall is mcx square by A. Now let's suppose that the total number of gas molecules inside this container is eta. So the average force experienced by the wall ABCD due to all these molecules would be here eta is the total number of gas molecules and A is the length of container. Now we can replace Cx square with C square by 3. So the average pressure which is being exerted by this gas molecule on the wall ABCD would be force by area of this wall, that is B into C, where B is the width of the container and C is the height. So this is our pressure. So we can write now pressure is equal to force, that is nmc square by 3 into BC. Now ABC is nothing but the volume of the container, so we can write pressure is equal to eta into m by 3V. Now suppose that there are n moles of gas inside this container, so number of molecules would be n into n, where capital N is the Avogadro number. So the value of eta, that is total number of molecules, would be n into n if there is n moles of gas inside this container. So we can write P is equal to n into capital N into m by 3V. Now m is the mass of one molecule. We know that the mass of Avogadro number of molecule is nothing but its molecular mass, that is capital M. So the mass of one molecule would be capital M by Avogadro number, that is capital N. So we can again rewrite P is equal to n into n. We can replace m with capital M by n into 3V. Now we can cancel out capital N. So now we are replaced with n into m by 3V. Now the ideal gas equation says that PV is equal to nRT, or 1 by V is equal to P by nRT. So we can replace V with 1 by V with P by nRT. Where P is the pressure. Now Pm by RT is nothing but the density of the gas, that is rho. So now we are left with rho by 3 into C square. Sorry, we left C square here. So finally we get the pressure exerted by gas molecules on a wall as P is equal to rho by 3 C square, where rho is the density of gas and C is its root mean square. Now we'll start the chapter thermodynamic process. So first we'll see what is a thermodynamic process. When thermodynamic state of the gas is changed from one particular state to another, the path followed by gas on state diagram from initial state to final state is called thermodynamic process. The mathematical equation which represent this curve between state variables, which is commonly taken as between pressure and volume, that is P and V. So that mathematical relation representing the curve on the state diagram is called process equation. So as we know that infinite number of curves can join the initial thermodynamic state and the final thermodynamic state, so therefore there can be infinite processes between two states. So for example, suppose we have a thermodynamic relationship between state variables pressure and volume. So suppose we are plotting pressure on the y-axis and volume on the x-axis. So at any particular point, say A, there will be some value of pressure and volume, say it is P1 and V1, and there is another point B where the value of pressure and volume is P2 and V2. So any path which join these 2 points, that is this will be the initial state and this B will represent the final state. So the curve which is representing the change of thermodynamic state from A to B, this is called thermodynamic process. So here P and V, that is pressure and volume, they are called state variables. There is another state variable which is temperature T. So we can take any graph between any two of the state variables, that is between P and T, or between P and V, or between V and T, but most commonly we use pressure versus volume graph. And as you can see that there can be infinite ways in which we can trace a curve between point A and point B. Say this is one of the curve, there can be another curve which can be straight line, there can be another curve. So what it means is that between two states there can be infinite number of thermodynamic process possible. Now we'll see different energies which are involved in the thermodynamic system. So first we'll see the change in internal energy. So as we know that the internal energy of a molecule is defined as F by 2 into nRT, where F is degree of freedom of that molecule, N is the number of moles, R is universal gas constant, and T is the temperature. So the change in internal energy, that is delta U, would be defined as F by 2 into nR delta T, and as we know from the gas law that nRT is nothing but P into V. So nR delta T, that is nR T2 minus T1, would be P2 V2 minus P1 V1, where T2 is the temperature in the final state and T1 is the temperature in the initial state. Similarly, P2 is the pressure in the final state and V2 is the volume in the final state. P1 and V1 are the pressure and volume in the initial state. So with this we can say that the change in internal energy, that is delta U, can be written as F by 2 into P2 V2 minus P1 V1. Now the change in internal energy is pure function of temperature, so it is independent of thermodynamic process. So it will only depend on the final temperature and the initial temperature. The change in internal energy is considered positive when there is increment in it. So suppose we have final temperature as T2 and initial temperature as T1, and T2 is more than T1, so we'll say that the internal energy has increased because the final internal energy is more than the initial internal energy. Now we'll see what is the work done by a thermodynamic system. So first let's suppose that there is a vessel having a piston. This is our piston, and inside this vessel we have certain gas filled. So if this gas expands, we say that it does work against external pressure, and this work is considered positive. So there is some pressure here, P pressure, and let's say after some time the gas expands, and let's say this height is h, and after some time the gas expands and this heights become h1, where h1 is greater than h. So we see here that the gas has expanded and it has done work against the external pressure P, and this work is considered positive. So while calculating the work done by a thermodynamic system, what we do is we assume that the pressure of gas at any instant is same throughout inside the gas, and the piston is in equilibrium with the external pressure. So we assume that the pressure inside the gas is also P, which means that it is in equilibrium with the external pressure, and this pressure P is same throughout the gas. So the work done by gas for small increment in the volume is given by dW, and it is given by P into dV, where dV is the small increment in the volume and P is the pressure of the gas, which is in equilibrium with the outside pressure. So to get the total work done, we need to integrate this thing. So the work done is nothing but integration of P dV, and in the PV diagram the area under the curve gives the work done by gas against external pressure. So suppose we have a PV diagram like this. So the area under this curve is this area. This will give the value of work done by the gas against external pressure. So this will be the work done. We can also supply heat to a thermodynamic system. The heat received by a thermodynamic system is considered positive, and the heat rejected by it is considered negative. So now we can define the first law of thermodynamics. This law says that the heat energy given to a thermodynamic system is partly consumed by the system in doing work against external pressure, and rest of it increases its internal energy. So suppose we have a thermodynamic system that is a gas chamber which has a piston, and inside this chamber we have some gas. Now suppose we provide some heat to the system. This heat is dq. So suppose dq heat is provided to the system,